Thanks very much. So I wanted to introduce Tommaso and the collaboration we've been doing together. So at Horizon, we've had a particular view of how to approach quantum programming. And I think it differs quite significantly from many of the approaches that you may have seen in other talks during the conference. In particular, we think about quantum programming in a kind of top-down way. What does an idealized quantum computer look like? And for us, that's the marriage of both the classical control system and the quantum computer. So it's a classical system that tells the quantum computer what to do and receives results back from the quantum computer and performs computation concurrently with the quantum processor. So our programming languages that we've built, helium and hydrogen, they target this abstract machine, this kind of idealized quantum computer. And then we have built a kind of near-time runtime environment that can execute this code on today's hardware. And although this is kind of an odd approach to quantum programming, we kind of believe it's the right way forward if we want to get the full power out of the devices that are available. But one of the things it means is that it takes tasks like quantum error correction and just makes them another form of computation. They're expressible in our languages just like any other computation. And so I think, at least for us, we see this as kind of an ideal test bed for starting to experiment with things like quantum error correction. So I'm really delighted to be able to pass the mic over to Tommaso, who's going to talk about some collaboration we've had looking at quantum error correction using our stack and using the stack of Entropica Labs. Thanks very much.
Thank you, Joe. And thanks, everyone, for being here today. It's been another great Q2B. I mean, Joe has given a great introduction. I'll also add my thoughts and why I think this collaboration is actually incredibly exciting. So I look at it from the perspective of developers. I guess most of you are actually using quantum computers today. And, it's not really easy to code on a quantum computer. And if you think about future computations, if you think about using fault-tolerant quantum computers, today we have this we have this challenge, but also this great opportunity of building the software infrastructure that we are going to need to enable developers, to enable all of us to use quantum computers effectively. Okay, so just a few words about the companies. So we're both based in Singapore. Entropica and Horizon are working on complementary aspects of the stack. So Horizon is building Triple Alpha, which is an IDE to code, compile, and deploy quantum programs on multiple quantum computers. While at Entropica, we are building the software that you need to manage the fault-tolerant quantum error correction part of the stack. So there is this beautiful complementarity, and as you have heard throughout the conference, there's also a lot of focus on error correction at the moment in quantum computing. And what we want to do with this collaboration is to enable people to very easily deploy quantum error correction experiments on multiple quantum computers, putting together Loom, our product, and Triple Alpha. And what I will show you today is how you can do that. And actually, I also want to show to you a different way to think about quantum programs for quantum computers. So that will be the main part of the talk today. Okay, I don't think I need to say much about this sentence. Quantum systems are noisy. And we know the noise is, well, the main culprit of why quantum computers don't work as they should. If you have a whole bunch of physical qubits, even just a few errors can very quickly propagate throughout the whole register. And when that happens, the quantum computation doesn't return the result that you want. So the way we usually think about quantum error correction is you want to be able to measure the state of the qubits, you want to decode the results of the measurement, you want to understand what kind of error is actually happening on the quantum computer, then you want to go and correct them. But one of the big difficulties, which is usually ignored actually, in quantum computing specifically, is that a lot of the processes that are part of quantum error correction are themselves quantum processes, which means that you can introduce even more errors. And all of that makes quantum error correction incredibly hard. It's a very difficult thing to do on quantum computing. If you go and look at the quantum error correction zoo online, what you will see is that there are a lot of strategies available This was done a couple of days ago. It was 915 at the moment. I don't know if we have more today. But the reason why I'm putting the number out there is just to highlight the fact that we still don't know if there is a single strategy to perform error correction on quantum computers, which is going to be the winning strategy, whether there are multiple, and we don't even know if the winning strategy or strategies are among the ones that we have discovered up to date. Well, the good news is that quantum computers, the hardware, is getting better faster and faster. And we have seen the results from Google, from Quantinuum, from other hardware companies, demonstrating how you can run error correction schemes on real hardware. So we're getting to a point where we can correct errors faster than they actually accumulate. And this is fantastic, because it gives us the opportunity to go and test all of the strategies, all of these codes on real hardware, and see what works and what doesn't. But to do, we need to promote tools that favor testing, development, and deployment of quantum error correction schemes in an easy way. And that is the core of the collaboration between Horizon and Entropica. So imagine you want to run a quantum error correction experiment today. What do you need? Well, first of all, you need expertise. You need to know what you're doing. You need to know about the error correction schemes. You need to know how to code them up and how to deploy them on quantum computers. But the expertise is very scarce. You know, you might need multiple PhDs in quantum error correction, and this is a hard to find skill set nowadays, and it will remain difficult to find moving ahead. You also need time and resources. You need to write code that is specific to the hardware that you want to use, usually. You need to translate the quantum error correction schemes into the relevant details. So go from something that might be described at a mathematical level in the literature into a real quantum program. And there's usually a lot of interaction that you need to go through to make sure that everything works as it should on the machine. And then obviously you need access to the hardware. And if you want to use multiple quantum computers, that might mean rewrite the program so that you can connect to the different devices. Okay, well, that's a lot, right? And if you want to go through 900 plus strategies, test them and see how they work, this is obviously not scalable. I'm not saying anything that will surprise you here, but I just want to emphasize the fact that we need to have software tools, software procedures to work on quantum error correction, or any quantum program really, much more efficiently. In fact, if any of you is a developer, if any of you is writing code to run a quantum computer, usually this is what you would do. You want to write a quantum program, and a quantum program is made up of tasks and targets for tasks. So let me explain what I mean by that. Usually a program is literally a sequence of tasks, operations that you need to perform on a computer. But then these tasks are defined at a high level. For example, you want to run a Fourier transform, a quantum Fourier transform, or you want to measure stabilizers in case of error correction. Then what you need to do, you need to define the targets of the tasks, what qubits you're performing these operations on, and so forth. And today, with pretty much all programming frameworks that are available, you need to do everything for each quantum program. Can you still hear me, Mike? Okay, thank you. You need to do everything within the same quantum program, which means that if you want to test multiple error correction codes on multiple quantum programs, you need to rewrite the tasks and you need to redefine all the targets, which is quite painful. Well, what if we do things differently? With triple alpha, what you would do, you define the quantum program in terms of tasks. And the tasks are defined at a high level, which means that you can reuse them. What we are doing here is modularizing the way you think about quantum programs. Then with Loom, Entropica's product, in this case, to define error correction codes. What you do, you define the targets. For example, you take the surface code, you define the elements that you need for a surface code. And then you transfer all the information using ECA, which is a data structure we develop at Entropica to define error correction codes. And you pass it to triple alpha. I'm sure you can see the value of that, because you define the program only once. Then you quickly define for the error correction codes. So this is how it will look like. These are snippets of code from triple alpha. For example, if you want to run a quantum memory experiment, you can easily define in a few lines of codes all the tasks that you need. You want to execute the quantum operations, you want to collect the measurement results, call the syndrome decoder, and so forth. So you define these once. And then you use the loom to define all the targets, all the tasks. And those might be the placement of the qubits, meaning the placement of the physical qubits on the device, the kind of stabilizers that you want to use for the surface code, for example, or other codes, how the circuits looks like, the context of the measurement, the graph for the decoding part. Then you export it as an ECA, which is a data structure, and you translate it into hydrogen, into an hydrogen file. Hydrogen is one of the languages within triple alpha. And this is incredibly neat, because then when you put it all together, now here you can see the triple alpha IDE. Jingao is our head of product at Entropica. So, well, in this example, he was the one running the code. It's actually quite fantastic. You start the quantum program, so you have the tasks that I just described, and on top, you just include an hydrogen file, which comes from the loom, and that includes all the data that you need for the error correction scheme. So you have produced this independently, and then you just append it to the program. This is how a developer would think and would work in the context of classical computing. And really, the message here is that we should start giving people tools to work with quantum computers in a way that is very familiar to anyone who's writing software, who's writing code today. And then all you need to do, compile and deploy. So it compiles the program, and then it deploys to different backends to multiple quantum computers using API calls. Let me emphasize again the point. You can define multiple quantum error correction schemes quickly with Loom, and then you don't need to change anything in the quantum program. You can just append it and run, and deploy on multiple quantum computers. So 900 schemes is a lot, but this workflow takes you closer to having a way to actually work very quickly and test, in this case, quantum memory experiments really quickly on multiple quantum computers. So there's one last thing that I would like to show to you, because this is actually quite nice. So it was still Jingao working here. What he did, using the AWS simulator backend, he actually ran a simple repetition code quantum memory experiment. It does everything I have just shown to you, deploys on the simulator backend, and then what happens is that the program now is waiting for the decoding result. So it stops the program. Then the information goes back to Jingao in Singapore, because the decoder, the decoding part was actually on his laptop, returns a result, and then the program starts again. This is an example of an adaptive quantum circuit. And in error correction, this is how, well, in any quantum computation really, but in error correction specifically, this is how computation are going to look like. Of course, here we are using a simulator, so it's not exactly the real thing in a way. But what I want to emphasize is that we can work in this way using existing software tools. We can implement adaptive quantum circuits already. We have all the structure to do so. So this is actually something very neat. So let me conclude. We're building automated workflows. So this collaboration really is aiming to demonstrate how you can quickly run quantum error correction experiments using Loom and triple alpha. And the goal is to unlock the potential of quantum. Now, there is still a lot of work to do, because we want to optimize the API workflows. We want to make sure that everything works smoother, faster. Well, in this particular example, we don't necessarily want the results to go back to Singapore, but we would like to do everything next to quantum computers. That's okay. But we can already deploy across multiple backends. It gets very easy to experiment with quantum error correction schemes. And obviously, the big goal is to move beyond these, let's call them proof of concepts, quantum memory experiments, but really work with programs, with full quantum programs, where you can do the same thing I've just shown to you, embed a quantum program into an error correction code, make it fault tolerant automatically, deploy it across multiple backends, which is what developers will want. So, to conclude, if you think this is interesting, as I hope you do, come speak to me, come speak to Joe, or you can contact us at the emails, and then we can chat together to really see how we can help you to work better with quantum computers, how we can help you if you're a quantum hardware company to move closer to having a system that enables fault tolerance. And if you're interested in use cases, equally, please come and talk to us. Thank you so much.
We have time for a few questions.
Hey, thank you.
No worries.
I'm just thinking, like, looking forward to the future and wondering a bit more how you guys are thinking about fault-tolerant logical gates, especially how they might interplay. Like, maybe I have a program that uses a lot of specific rotations, and there might be a certain code that implements those rotations more efficiently. Like, I'm just curious for you to elaborate a bit more about how this is going to think about fault-tolerant gates.
Sure. This is a great question. I'm sorry. I wanted to see who was speaking. This is why I'm covering the very bright light in my eyes. It's a great question. And the way I'm thinking about that, which is part of the motivation for this kind of work, we want to have ways to really quickly and easily test what works well and what doesn't work very well. So to me, if we have the capabilities to, I think it's fair to say, and you can correct me if you disagree with the terminology that I want to use, if we can look at how to co-design codes, or let me say programs that bring together applications and quantum error correction codes, which also include the information about the hardware that you want to use, well, that's great. This is exactly what we want to do. And everything we're doing here is to facilitate the kind of exploratory work. It's really as simple as that. We want to, in the next few years, it's going to be about experimenting, testing, and finding out what works really well for what hardware, for what application. And it is also an exploratory problem. And it is the kind of problem that doesn't scale very well if you do manually. You want to automate as much as you can. It was a great question. Thank you for that.
Yeah. Anyone else? Okay. If not, let's thank our speaker again.
Thank you.